Hi all, today we discuss section 2.3 linear independence. So this is the consequence of the concept of linear combinations. Last class we have discussed a vector, uh, the linear combination of two vectors. Say if you consider a vectors 1 0 0 and 0 1 0 in R3. Then when you consider these two vectors, you can say that this 1 0 0, when you consider the linear combination of this vector, so the linear combination of this vector is d times 1 0 0 for all d belongs to R. So when you consider this 0 0 1 as a linear combination of this 1 0 0, if this happens, we can get this d is equal to uh, 0, that implies uh, uh, 0 0 0 equal to, when you put d is equal to 0 here, you can get 0 times this. So 0 1 0, this is a contradiction. That means this vector 0 1 0 is not a multiple of this 1 0 0. Okay, or 0 1 0 is not a linear combination of 1 0 0. Okay, similarly you can do the other thing. When you consider the linear combination of 1 0 1 0 as c times 0 1 0, that is equal to 0 c 0, this implies c equal to 1 here, then that is equal to, I'll write it, this is in the other form, I'll write it as, this is c times this, that is a linear combination of 0 1 0. We need to verify that 1 0 0 is an element of this span, okay, or is that an element of linear combination, okay, of these two 1 0 0. From this you can write c is equal to 0. Consequently you can get 0 0 0, that is 0 times this vector, that is equal to 1 0 0. This is a contradiction because when you compare these two terms, you can get 1 equal to 0, so that is not possible. That's why this is a contradiction. So we can say that this vector is not a linear combination of this vector, and this vector is not a linear combination of the other. Okay, then what is the importance of this? Once you got these properties for two vectors u and v, you can say that whenever you write c1 times that u, if you take this is u and this is v, you can say that c1 times u equal to so c1 times u plus c2 times v is equal to the 0 vector. This is 0 vector, implies c1 equal to 0 and c2 equal to 0. Okay. Otherwise, what happens when c1 not equal to 0? You can write this from this expression. You can write this c1 u is equal to minus c2v. Consequently, this u will be considered as minus c2 by c1 times v. Okay. So whenever c1 not equal to 0, you can get v as a u as a multiple of v. Okay, when c2 not equal to 0, you can get v as a multiple of, you can write it as this form u. If this happens, you can say that v is a multiple of u. If c1 not equal to 0, you can say that this u is a multiple of v. Okay, but we have proved that this one is not a multiple of the other in any case. So then this holds. Okay, both the coefficients should be 0. The generalization of this concept is called the linearly independence. Okay, so this is only for two vectors. So we can extend this property. That is, then we can define the linear independence of the vectors. Suppose we have v1, v2, etc. vn. These are all elements of a vector space V, and consider the linear combination v1 plus etc. Cn vn is equal to 0. Once you got by assumption of this c1 equal to c2 equal to all the coefficients are 0, then we can say that v1 v2 etc. vn are linearly independent. So this is a definition. 2.3 starts with a definition of linear independent vectors or independent vectors. Okay, so this is the definition of linear independence. Then what is the linear independence? Definition of linear independence? When you assume C1 times C2 times etc. Cn times Vn is equal to 0, implies each coefficient equals 0. So the linear combination must be 0 only when all the coefficients are 0, otherwise not possible. Okay, so you can define the linear combination the other way. If in order to say that this V1, V2, etc. Vn are linearly independent, if one of this any of this vector cannot be written as a linear combination of the others. Okay, you cannot write any of these Vi as a linear combination of something times V1 etc. something times Vn, okay, except this Vi. Okay, so you cannot write any Vi as a linear combination of the other. This is not possible. Then only we can say that this these vectors V1, V2, Vn are linearly independent. So this is the definition. The definition is the set of all the set of vectors V1, V2, etc. You can write it as set V1 set of vectors V1, V2, etc. Vn is a subset of V, is linearly independent if C1 times this equal to 0 implies each coefficient is 0. Okay, so this is the definition. For an example, you can consider this question. These two U and V are linearly independent. We have already proved that whenever this is equal to 0, you can easily prove this condition using this definition. When you assume two vectors are elements of R3, then you consider C1 times this 1, 0, 0 plus C2 times 0, 1, 0. We need to assume this is equal to 0 in R3, it's a 0 vector in R3. So this implies, what is LHS? LHS is this sum. So that will give C1 comma C2 0, C1 times this, that is the first component will be C1, here the second component will be C2. When you add this, you can get this is equal to 0. Consequently, by equating the coordinates, you can say that C1 equal to C2 equal to 0. So now we verified the definition. Whenever C1 times V1, C2 times V2 equal to 0 implies each coefficient is 0. This shows that these two vectors are linearly independent. Next we have a theorem. A finite set of vectors is linearly dependent, not independent, if and only if one of the vectors is linear combination of the vector that precede it in the ordering established by the listing of vectors in that set. That means if you choose a set of vectors v1, v2, etc. vn with an order v1, v2, etc. vn, which is a subset of V, a vector space V, and this is dependent vectors in dependent set. Okay, if and only if you can write any of these vectors, one of these vectors, not all, but there exists such Vi that is a linear combination of V1, D1 V1 plus etc. D Vi minus 1 Vi. So this is possible for some vectors. Okay, so to prove, we first assume this V1, V2 etc. Vn are linearly dependent. That means there exists a linear combination C1 V1 plus etc. Cn Vn equal to 0, but not all, here not all 0 with scalars. Ci's are scalars, not all 0. Scalars not all 0. Okay, that means there exists some non-zero scalars in this expression. Okay, choose the last one. Okay, choose let Ci be the last non-zero scalar. We name that as Ci. The Ci can be Cn if Cn is non-zero. If Cn is 0, then we will verify Cn minus 1. If that is non-zero, then Ci is Cn minus 1. If Cn minus 1 and Cn are 0, then take Cn minus 2, the previous one. Then name it as Ci. That is, Ci is the last non-zero coefficient. That means Ci is non-zero, but we can say that Ci plus 1 equal to 0. All the rest of the remaining coefficients are 0. So this is the selection of the Ci. The Ci can be anyway. Ci can be Cn. At that time there will not be the Ci plus 1, etc. So if this happens, you can write this expression as C1 V1 plus etc. Ci Vi 0 times Vi plus 1 plus etc. C and 0 times Vn equal to 0. This implies this part is 0, then Vi can be written as minus C1 by Ci times V1. This is Vi here. Vi can be written as minus C1 times Ci V1 plus minus C2 by Ci times V2 plus etc. The last one will be Ci minus 1 by Ci, negative of that, times Vi minus 1. So this shows that this Vi is a linear combination of the preceding vectors V1, V2, etc. Vn, if this is the ordering. Okay, so this shows that one part. A finite set is linearly independent, then this happens. Conversely, assume that there exists a vector Vi belongs to the set V1, V2, etc. Vn, and this Vi is a linear combination of some d1 V1, the preceding one, C1 d1 V1, etc. di minus 1 Vi minus 1. That means there exists one of the vectors which is a linear combination of the preceding vectors, if this is the order V1, V2, V3, etc. Vn. Then what happens? Then we can write an expression d1 V1 plus etc. di minus 1 Vi minus 1 plus 0 times this, or minus times. When you take this in the other side, you can write this as Vi can be transposed to the right side. Then that will be minus 1 times Vi plus 0 times Vi plus 1 plus etc. 0 times Vn equal to 0. When you transpose this Vi to the right, so you can get an expression whose coefficients not all 0, because this is a non-zero coefficient. So by putting non-zero coefficients, you can get this expression is equal to 0. This implies V1, V2, etc. are Vn are not linearly independent, that is linearly dependent. Okay, this proves the other part. So this completes the theorem of the characterization of linearly dependent vectors. Okay, the next class we will discuss other two theorems regarding this this linearly independent and dependent vectors.